What if we had infinite compute? A paper out of Stanford asks this question. I think it's an interesting question, although I don't think that we will have this type of situation anytime soon. But just conceptually, what the authors are asking here is imagine if we build out this infrastructure the way we are, and we have really much more compute available than relative to the data. In other words, we have a fixed data block of, let's say, internet data, and then we have infinite compute. What can we do? How can we improve training, and how can we improve our models? The answer of the paper is there's two things you can do. One is regularization, the other is ensembling. But I think besides the empirical findings, which of course are important, I think it's worth thinking more deeply about this actual question. It's not even on podcast. It's October 6, 2025. This is Krim Telco. For the day, we're up 5%. The market's up 40 basis points. For the year, we're up 19.2. The market's up 14.7. We're outperforming by 4.5%. So this paper, basically, the actual title of the paper is, one sec, sorry, Pre-Training Under Infinite Compute. So this is a very high sort of LLM type paper. We're not bringing in Richard Sutton here. We're not bringing in continuous learning. We're just asking ourselves, okay, in this pre-training regime that we live in, what started with ChatGPT and now has morphed into this massive AI frenzy, how can we think about this conceptually? And I think it's very interesting. What the authors are asking themselves here is, what if we had infinite compute? In other words, what if compute outpaces the availability of data, of useful data, right? Now, people might ask, well, what are you talking about? We have synthetic data, we have continuous learning, we have RL, we have synthetic data creates new data, RL creates new data. We will never run out of data. Let's put that aside. Let's just think, okay, we have a fixed data block here, and how can we improve training? So this is a hardcore, this is a Percy Liang paper, together with other links in the show notes. What they're asking is, okay, look, let's just assume we have infinite compute and we have a fixed block of data. How can we improve? And the two things that you can do is regularization and ensembling. And what that means is regularization just means that you really knock out high weights. So you make sure that the model is as diverse as, there's no bias in the model. There's no, like, it's trained on really, like, tall black center backs are better, and they dominate any kind of model that predicts success in soccer or basketball, or things like that. Like, you try to make this model less memorizing and more actually intelligent, meaning more trying to understand intricacies from relationships than just pure size. So regularization just knocks out high weights. They find empirical data that helps. The other is ensembling, which is actually an interesting thing. I've never heard of it. It's something that researchers obviously are familiar with. What that means is ensembling just means that you take a block of data and you use the same model, but you kind of shuffle the data and you train several times. So you let's say you use different initializations. You maybe you use different rankings of how you feed the data. Maybe you have different types of memory constraints or batch sizes, like things like that. But the model architecture is the same. What you're trying to do here in the analogy would be that you're looking at the performance of a certain data set, or you're trying to make sense out of a certain data set, and you're using several experts, and then you're kind of averaging out their predictions. What's interesting here is that they find that there's a certain size of ensembles up to 5, so 5 training runs with the same models, but different data mix that actually improve performance. After that, correlation starts kicking in and performance deteriorates. So the goal of this paper is to get more juice out of what we have, and particularly if data is constrained. Now, I personally don't think that is a problem. I think this is a little bit short-sighted, maybe from this group, to even think about this, but it's okay. I mean, you learn nevertheless, and this is science. Because I don't think that we are data constrained. I think data is it's kind of like we spoke before, like what we are really constrained is goals. Like we have to set goals, and the data that we have at our disposal is the usefulness of data is directly related to how good the goals are. So if we set good goals, like for example, getting to Mars is a good goal, and we have plenty of data to learn from to get to Mars. We might be a little bit too early. Maybe we need a few technologies to evolve, but we can do that. Like we have, we have to set ourselves goals, whether it's big goals like going to Mars or smaller goals like, finding the best possible recipe for a certain material to improve a battery technology. The goals are really what constrains us. It's not the data, and certainly not the compute. I think we can build the compute, at least in the context of where we stand today, with the semiconductor technology that we have, with the interconnect technology we have, with the software know-how that we have, that is proliferated by NVIDIA and also by AMD and others. I think we have enough knowledge to push this field further. At some point, we might want to converge into more advanced compute technologies like quantum computing. But again, like if we had, let's say, if tomorrow we had a quantum computer that 100, 1,000, 1,000,000 X's our compute capacity for certain problems, we still would not have, we would never run out of data, because we would generate a lot more new data. We would generate, particle physics, like how particles interact, Ising model. We improve the Ising model. We do RL on the Ising model, which produces new data. We can get more granular. We can get more, a lot more interesting insights. So this concept that we're data constrained, I think, is a bit like a Malthusian view of data, and I don't think it's valid. Thank you.